learning with constraints or constrained learning. So that's a bad place for this, maybe here. Okay, good. So the idea of constraint supervised learning, which is the first topic that I want to introduce, is more or less, I would say, exactly what you would expect it to be. So in a typical machine learning problem or a typical artificial intelligence problem, whatever way you want to call it, statistical losses appear as objectives. So here you have your learning parameterization that parameterizes a function phi. You pass that through some loss, you take the expected value of that, and that's the quantity that you're trying to minimize. You're trying to maximize the fit between your data and your learning parameterization. In a constrained learning problem, as you would expect, you also have some statistical losses that appear as constraints. That's one possibility. A possibility that is perhaps a little more obscure, but equally interesting, I would say, is that maybe you also have some point-wise constraints that you want to enforce, right? So you want your loss to satisfy some condition for all possible realizations. I will give you examples of this later on. Now that's the constraint supervised learning. Alternatively, maybe you are more of a reinforcement learning person, and in which case you kind of formulate problems with the same flavor. In a regular reinforcement learning problem, your goal is to maximize some objective reward. Actually, we collect rewards from the environment, we discount those rewards, and then we take expected value with respect to the state distribution and the action distribution, which is what you're actually training for. Okay, so these optimization problems are sometimes a little wicked to understand because the optimization variable is on the probability distribution. Anyway, so that's what we call the value function, and the idea is that we want to maximize this value function. In a constrained reinforcement learning problem, you also have some rewards that appear as constraints. Thus, in regular learning, you want to find a parametric function that minimizes some statistical objective loss while incurring, at most, C units of statistical constraint loss L and C units of constraint loss L prime almost everywhere over the data distribution. In constraint reinforcement learning, what you want to do is to find a policy pi star that maximizes the accumulation of the objective reward while accumulating at least CI units of constraint reward Ri. And typically you have several of these that you would like to satisfy. Just because later I want to simplify notation, I can stack all of these things into a vector and say that this constraint value function has to be larger than C, and this value function and this C are both vectors of appropriate dimension. Okay? Now these two are the problems that I want to solve. Let me, before I tell you about the mathematics, tell you a little bit about where these problems arise or why these problems are important. And I believe that there are three motivations or three reasons why you should care about requirements in artificial intelligence, all of which, by the way, are summarized by a simple statement here, which is that we all operate under constraints, right? So, there's several things I would like to be doing today, but I have only one life. So, if we operate under constraints, artificial intelligence systems should operate under constraints as well. And, that is tied to the maybe most clear motivation for the use of constraints, which is that we are often choosing to ignore, or actually, the tech companies choose to ignore for us the glaring limitations of AI. And those glaring limitations are that we not only want to feed data as best as possible, we also want to be safe, robust, fair, representative, truthful, a number of things that you would like to impose in your AI systems that we typically do not. And well, what happens, happens. As an example of that, let me point you to this work that we have done on the alignment of generative large language models to user preferences. In a large language model, what you train is a probability distribution. That probability distribution takes prompts as input. It produces text as output, okay? And the generation of that data here is through a probability distribution that is parameterized by a transformer, okay? So when you hear about an LLM, this is what you're hearing is a probabilistic distribution that takes a prompt as an input. It produces some text as an output, and that output is generated by a probability distribution that is parameterized by a large scale transform. You could think that you are given some pre-trained policy, which here will become some kind of reference. And given that pre-trained policy, you would like to find another policy by theta, that's your optimization problem, such that some kind of reward gets improved. And those rewards are what you are going to utilize to align this pre-trained model, which is not yours, to your own personal user requirements. Okay, like for example, you may want to say that you want to align a pre-trained model, a pre-trained large language model, to enhance its helpfulness and safety on the text that is generated in response to prompts. Okay, and yes, that's what we have done. And there are several curves here that illustrate the performance of this algorithm. The most important of which is here in the middle. So what I am showing here is the Pareto front of helpfulness versus safety. And if you utilize learning with constraints, this Pareto front is pushed in the right direction. So here you have also changes in the safety score, and you see how the safety score is pushed up. Here you have changes in the helpfulness score, and you also see how the helpfulness score is pushed up through the addition of safety and helpfulness constraints that you're utilizing to align the pre-trained model to your own personal preferences. Now, that's an example number one. It falls under the category of not ignoring limitations of AI, right? I mean, not ignoring the fact that this AI is producing unsafe outputs and actually training or retraining to ensure the safety of the LLM. A second motivation, which I think is equally interesting, although a little less easy to see, is that very often problems that do not look like constraint learning problems are often easier to formulate using constraints. And an example of this is this idea of composing generative diffusion models. Now, for those of you that don't know what a diffusion model is, it's actually something that signal processing people should understand very easily. So here we have a noising process, and here we have a denoising process. In the noising process, we have noise to images in the training set or data in the training set in general. And in the backward process, we learn or we train a denoiser that is reversing this Markov chain. Okay, and this is a good idea because the distribution Px0 is a very complex distribution, but each of these noise distributions are very simple Gaussians, and therefore each of these denoise distributions, each of these conditional distributions are not difficult distributions to learn. Anyway, so what we want to do is learn this denoiser, which is going to lead us to some learned distribution P of x0 epsilon theta. The composition problem refers to the training of a model P that is close to a number of pre-trained models that have been given to us. Okay, so you can think of this as, there are several diffusion models that are available for you in the market. You can buy, or actually not even buy. I mean, these things are in the public domain, right? So you can download all of these different models, and you would like to leverage all of them. So you would like to have a model here, P, that is able to sample from all of these different pre-trained models. Now, this problem typically is formulated by, training some kind of weighted average of KL divergences. But then the question is, what are the weights that you should put in these different KL divergences? You can avoid this problem by formulating this optimization problem. Okay, so this, again, falls under the category of a problem in which constraints are not obvious, but that you can nevertheless formulate with constraints more naturally. And the idea here is that I can restrict all of these KL diversions to be smaller than U and minimize that U. So this is very arguably the best possible process that you could train. The reason for that is that this composition of models is going to be as close as possible to all of your pre-trained models. Okay, so let me repeat that. What this formulation is doing is the following. I compare the distance of my model to all of the pre-trained models, and I want to be, well, I want to minimize the worst case distance to all of these pre-trained models. And this is useful because here is an illustration of what can happen if you don't do that, which is that some of these models will have overlaps. And if you do not make worst case formulation, you're going to end up sampling more from the overlap of these distributions. Okay, anyways, another perhaps a more important plot is shown here. So this is if we combine utilizing equal weights, and you see how some models are being preferred over other models. However, here, when you train with constraints, you are equally close to all of these different models. Here, you have your customary pretty pictures to show that through the use of constraints, you actually end up obtaining things that look prettier. But there's some couple of other interesting things here. Like, for example, this one shows you that when you train with constraints, the distance to the pre-trained model upon convergence of your algorithm tends to be smaller, which is an indication that you have actually succeeded at retraining this pre-trained model with little deviation. Okay, now I covered two examples of applications of learning with requirements or learning with constraints. These are not ignoring limitations of AI. The second one is problems where constraints appear, although not very naturally, but nevertheless in a useful manner. And now let me get to motivation number 3, of which I'm going to give you 2 examples because that's my favorite motivation, which is the use of artificial intelligence in physical systems, okay? Because physical systems, as I'm pretty sure we all know, are designed to satisfy requirements first and to be optimal second, okay? And in case you don't know this, here is an example of a wireless communication network. The quality of service is determined by the SINR, and these are the kind of problems that we formulate. We want to maximize some network-wide utility subject to individual quality of service requirements and individual power budget requirements. And mathematically, if you want, that's the formulation of this problem, but it doesn't really matter what these equations are. What matters here is that this is your cake and this is your sharing, okay? So when you design a physical system, what matters to you are constraints. The optimality criteria is important, but secondary to the satisfaction of constraints. If you violate your constraints, your customers are pissed, right? If you violate this constraint, your power is, well, you don't have enough power in your system to actually be communicated. If you have your customers happy and you are satisfying your power constraints, then you can optimize. And that makes the current practice of AI somewhat mismatched to physical systems. Okay, why? Well, because current practice of AI is focused on minimizing losses, and here we want to solve this constraint optimization problem. Anyways, to solve this problem, we have been working on learning resource allocations. Learning resource allocations in wireless communications is actually challenged by the fact that the optimal resource allocation policy is stochastic. That requires that we use some weird technique, which we call data augmentation. I will explain this later on. But at the end of the day, what matters here is this. Here you have 3 other learn policies. Here you have the policies that is learned with constraints. These are your requirements. So, this is, in a sense, the only policy that is workable because it's the only one that actually satisfies your requirements. Alternatively, by the way, since I already talked about diffusion processes, you could go ahead and train a diffusion process instead of doing this state augmentation. It will give you this very interesting policy distribution. I do have one other example, one other motivation, which is, again, along the lines of physical systems, but this is a different example, which is the solution of optimal power flow on power distribution grids. There are people here that understand this problem way better than me, so I am going to try not to embarrass myself. But in optimal power flow, you want to solve this optimization problem. Again, those equations don't really matter much to what I want to say. I can abstract all of these equations into this constraint optimization problem. You want to minimize some cost subject to some requirements, and you have inequality constraints and equality constraints. And the thing that matters here is that these constraints over here, these are physical power flow constraints, okay? If you violate these constraints, you are breaking your grid. In terms of machine learning solutions or artificial intelligence solutions to this problem, you can formulate this problem with statistical constraints, or more importantly, or more suitably, I would say, you can formulate this problem with pointwise constraints, right? Because you don't want to satisfy constraints on an average of system realizations. You want to satisfy constraints for all individual realizations. Make sense? Right, so these constraints here, I don't want to satisfy them on average across realizations of the system. I want to satisfy them point-wise for each individual realization of the system. Okay, so this is the only example I have here in this talk of a problem with point-wise constraints. If you go ahead and you train a graph attention network on IEEE 300, we have results for other networks in our paper, you will see something very interesting happening here. So on the y-axis, I have optimality. On the x-axis, I have relative constraint violation. And you see here that the use of pointwise constraints give you policies with 5% constraint violation. Each point here, by the way, represents a different network realization. And if you apply other learning techniques, you end up with something like a 50% constraint violation, which is completely unworkable. And the reason why the constraint violation here is so large is because I am focusing here on the worst possible constraint violation. And since I have a large number of constraints here, you will always be violating some physical constraint by a large amount unless you specifically train to satisfy constraints. Okay. Now that's the first part of the talk, where I wanted to tell you a little bit about what learning with constraints is and what are the applications of learning with constraints. I want to spend a few minutes talking about challenges, and then I will dive into the mathematics of how these problems can actually be solved. Okay? The challenges here actually are, well, maybe what I suppose a lot of you would guess the challenges are. Let me focus for the rest of the talk on constraint reinforcement learning. Constraint supervised learning is very similar. And here I am repeating the problem for your reference. I am trying to maximize this value function subject to this value function requirements. And again, I'm going to use this vector notation. Now, the first challenge that you will face in constraint reinforcement learning is that these value functions here, B0 and B, are not convex. Okay, and I am showing you here a picture because there are some papers there that claim that these value functions are convex. Those papers are wrong, and these figures tell you that. Now, being non-convex means that you cannot really move into the dual domain, but let's set this problem aside for a minute and let us actually move into the Lagrangian dual domain. And in the Lagrangian dual domain, I can write B0 pi plus lambda transpose B minus C. And what is remarkable about operating in the Lagrangian domain is that when I attempt to compute the dual function is a standard unconstrained reinforcement learning problem. Okay, so that's the reason why we incorporate, that's the reason why we want to utilize duality. We go from constraints to unconstraints, okay? In which, the reward now is this linear combination of objective and constraint rewards. Now, the dual problem, for those of you that haven't heard of that, is the minimum of the dual function. Now, what we know is that the maximization of the Lagrangian, as I was telling you a minute ago, is a standard unconstrained reinforcement learning problem. And that's the reason for using this dual formulation, right? So that's the reason why we would like to solve the problem in lieu of the optimal constraint reinforcement learning problem. Now, however, in general, non-convex problem, dual maxima are strict upper bounds of primal maxima. Okay, so this duality gap is positive, and actually this duality gap can be terribly bad. So it could be that this proxy here is a terrible proxy for the actual solution that I want to compute, which is the solution of the constraint reinforcement learning problem. So that's the first challenge. The answer to this challenge is that I'm going to explain to you in a minute. This does not happen. Constraint reinforcement learning has zero duality gap, despite the fact that these functions are not concave on pi. Now, the second challenge that will arise has to do with algorithms. And algorithms, I'm not going to explain why they are challenging now, but believe me that they are not. And in order to design an algorithm for constraint reinforcement learning, I will introduce this idea of state augmentation. And finally, a third problem, which will be obvious after I mention it, is that nobody has told me that these requirements are satisfiable in my system. And for that reason, you would like to have some kind of automated mechanism for you to be able to adapt these requirements. And we will do that, borrowing from economics, as a matter of fact, by introducing these equilibrium conditions in which we equate marginal costs and benefits of constraint relaxations. Anyways, that's a sort of preview of the three things that I want to cover in the next 30 minutes of this talk. Okay. I've been talking for a while, right? So I have a rule when I teach my students that after 20 minutes, you guys are tired of me. So I should give you a break. So I hope that you're not very tired of me, but the break is here. I mean, let me give you a summary of the important facts that I've been covering so far, okay? I've told you about the use of constraints in supervised learning and reinforcement learning. In both cases, the idea is that I have statistical losses that appear not only of the objective, but that also appear as constraints. Okay, you may wonder why in the world do I want to cover, or why in the world do I want to study these problems? I think that there is very ample evidence that this is necessary. Okay? First off, AI is full of problems that we are choosing to ignore. We should not ignore them. These things don't need to be unsafe. These things don't need to be biased. These things, they don't need to hallucinate. We can design them to avoid these problems. We just need to enforce that requirement. Furthermore, there's some interesting problems where constraints arise in a useful manner. And perhaps most importantly for me, in physical systems, which I think is an underexplored application of AI, constraints will arise naturally, because in physical systems, we don't design for optimality, we design for satisfiability. Now, I then moved on to tell you about how I will solve these problems, and naturally, I want to solve these problems in the dual domain, okay? So that's kind of like out of the question. I mean, I wouldn't know how to solve these problems without operating in the dual domain. However, operating in the dual domain is not easy. First off, there's no convexity, which means that there's the potential for a positive duality gap. Second, algorithms are not, what the algorithms should be is not obvious. And third, what the constraint levels themselves should be is not obvious. And let me now move on to address these three different challenges. Now, to cover the first challenge, I mean, I'm not going to make a mystery out of that. There's a theorem here that tells you that these problems have zero duality gap, okay? Now, I need, however, to tell you a little bit about why this result is true. Now, this result is true because there is an equivalent formulation of reinforcement learning in terms of what we call the occupancy measure, okay? And again, without entering into details of what the occupancy measure is, what happens is that when you formulate the problem in occupancy measure space, the problem is linear with respect to your policy, okay? It's infinite dimensional, but linear. Being linear, it has zero duality gap. And you could say, well, since I have problem 1 equivalent to problem 2, and problem 2 has null duality gap, well, it should be possible for me to prove that problem 1 also has null duality gap. Okay, let me go again. So here I have the problem formulated in policy space. Here I have the problem formulated in occupancy measure space. And these two problems are equivalent. Therefore, maybe I can conclude that since the problems are equivalent, and this one has no duality gap, this one shouldn't. That's not quite true, because here is an example of a problem in policy space, and another problem in occupancy measure space. The problem in occupancy measure space is linear, so this epigraph formulation is a polytope. This one has no duality gap, but the other one does not. However, in these equations, there's something I didn't tell you, which is that actually you can show that the two epigraphs are the same, okay? And therefore, because the two epigraphs are the same, D equals P, blah, 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 okay? Good. Now, very importantly, I need to explain to you what is that this theorem does not show, okay? So this is the epigraph formulation of the problem formulated in occupancy measured space. This is the epigraph formulation of the problem in policy space. In occupancy measured space, the problem is linear, okay, which means that the value function associated with a linear combination of policies is the corresponding convex combination of the value functions. Okay, so here I take the convex combination of the policies, value function, and here I take value function first, convex combination later. In this case, this is not true because remember, I showed you already, I mean, these value functions are not convex. What you know here is that there exists some policy that will trace the convex combination, but this policy is not the convex combination of policies. Now, you may think that I am being a little pedantic, and maybe you're right, but this will actually be very important when we want to design algorithms for solving constraint reinforcement learning. Okay? So keep this in mind. Just one caveat, by the way, I mean, we actually do not operate directly in policy space. We operate on a parameterized policy space. Never mind, you know, you can make assumptions on the parameterization to make it close to universal, and you can come up with bounds on the duality gap. Okay, so if you are operating in unparameterized space, the duality gap is 0. If you're operating in parameterized space, the duality gap is small and 0. You know, let's call this one the engineer 0. Okay, and we are all engineers here, so no big deal. Okay, now that was about the challenge of duality gap. So, you know, what I have shown you is that the duality gap is not really a challenge. Okay, so that's interesting. I mean, even though the problem is not convex, I can move into the dual domain. I can do that without no loss of optimality at all in unparameterized space, with a small optimality loss in parameterized space. Having moved into the dual domain, I can celebrate, throw a small party, because now, you know, I have this problem here, which is an unconstrained machine learning problem, an unconstrained reinforcement learning problem. An unconstrained reinforcement learning problems I know how to solve. Okay, you utilize your favorite algorithm here. You know, these days, favorite for most of you should be PPO. But whatever, you know, any policy gradient method will solve this optimization problem, okay, because it's unconstrained. Now, after you solve this unconstrained optimization problem, you proceed to update the dual variables, okay? And we update dual variables by evaluating constraint violations. And I should say here that I am writing lots of equations, which I'm glancing over them very quickly. I don't really want to learn the equations. Rather, you listen to me, but the equations are here for reference, okay? So what I am doing here is I am evaluating the constraint violation associated with the Lagrangian minimizers, maximizers, sorry, and I am using that to update my dual variables. So what am I doing here? Well, this is implementing dual gradient descent. And given that dual functions are always convex, this will converge to lambda star, okay? And if this thing converges to lambda star, you should expect a theorem like this one to hold, okay? And this is what we call the ergodic convergence of a stochastic dual gradient descent. And I hope that Yorgo smiles here because I've been doing this for 22 years. I started doing this kind of things in Minnesota. So this is ergodic convergence. Okay, ergodic convergence is the thing that I've been doing since my PhD years. And what does ergodic convergence mean? Well, it means that if you take the average of the value functions, the ones that appear in the constraints, they will be feasible, and they will also be near asymptotically near optimal. Okay, this is what you want. I mean, you want to satisfy your constraints and you want to be close to the objective. But there's a very important caveat here, which is that the average is on the outside of the value functions. And what you would like is to prove this conjecture. which I am adjudicating here to time immemorial. That's a joke because I don't want to cite the papers that prove this theorem, okay? But the tantalizing conjecture that you would like to prove is this one. I can get those average and send them inside of the value function. But if you remember the epigraph that I was showing to you, you cannot do that, okay? So that's kind of a significant impasse, right? Because I am presenting here an algorithm which has come very close to working, but doesn't quite work. And furthermore, I have told you that this is the only way in which I know how to solve this problem, okay? So, you know, this is like a Cinderella's story. So right now we are about the time in which we are losing our sleepers, I think, right? So this is the bottom of the hole of this talk, because, you know, I've been building towards this and now I'm telling you, I don't know how to solve this problem, okay? There will be, of course, a workaround because in the end, I am Prince Charming, so I'll come to the rescue. That's a joke. I mean, you're supposed to laugh at this guy. No, okay. Jokes aside, okay, yeah, but very important. Okay, so this I can prove, and by the way, it's not very difficult to prove. I would like to prove this, but this is just plainly false. You can actually construct counterexamples, and the reason it's false is because the value functions are not concave, as you will need them to be in this case. And again, right, I mean, the reason why this happens is because of the way in which this epigraph is convex. Okay, because the epigraph is convex, I can prove conversions with the averages on the outside, but I cannot prove conversions with the averages on the inside. Okay, so let me move to the previous slide and tell you where we are. So where we are is here. We began the day talking about learning with constraints, either supervised or reinforcement learning. That, as I have argued several times already, is a fundamental problem, I would say. I mean, mostly for two reasons, right? Which is that there are limitations of AI that we should not ignore. And second, I think that AI could be very impactful in physical systems, but not AI in its current iteration. In order to be able to realize learning with requirements, there are, however, challenges that we need to overcome. And those challenges are related mostly with the lack of convexity of these problems. If these problems were convex, I mean, this is like a standard convex optimization theory. Now, non-convexity in constraint learning is kind of like the least useful thing in the world. Okay, and bear with me for a minute, because you can write down constraint learning in non-convex problems, but you typically cannot solve them, unless in particular cases. It so happens that machine learning falls into those categories of problems that, even though are non-convex, they can be solved. And why? Well, because they have either null duality gaps or very small duality gaps. So that's the critical thing that I've been saying so far, that these problems, they don't have a large duality gap. Operating in the dual domain is near optimal. However, algorithms are not straightforward, okay? Because that's what you can prove. This is what you would like to prove. This is what you can prove. This is what you would like to prove. These two things are not the same. Okay, and that's what is summarized here. And as I like to say, alas, poor Yorick, dual gradient descent does not converge to the optimal policy. And I do want to point out that I have earned the right to cite Shakespeare. Let me then move on to the solution. The solution comes in the following form. Let me first change the problem into a simpler one, which is ergodic constraint reinforcement learning. I am not using discounts, but rather taking ergodic averages. And as usual, I'm going to utilize this vector notation. Okay. I am now going to propose this algorithm, which I will call rollout dual gradient descent, which for those of you that have worked on constraint reinforcement learning should know where rollout comes from. But in any case, I am doing an unparameterized policy optimization. Okay, so this is the maximization of my Lagrangian, and you know I can do that because the maximization of this Lagrangian is a standard constraint reinforcement learning problem. And then instead of updating through the dual function as I did before, I am updating directly on the sample estimate of the value function, which is just the accumulation of rewards. Now, this is an stochastic approximation of the gradient. Therefore, this theorem should hold. Okay, and actually it does hold. It's the same theorem as I wrote before, except that instead of writing it for gradient descent, I write it for a stochastic gradient descent. And again, what we have here is almost sure feasibility and near optimality. But again, I mean, we have these summations on the outside. And as I have already argued, I cannot send these summations to the inside. However, let us not underestimate what this theorem is telling us, because what it's saying is that the time averages of the rewards of the sequence generated by the rollout dual descent algorithm does converge. Okay, so in a sense, the sequence of policies that I generate are a solution of the CRL problem. As a matter of fact, that is stronger because constraints are satisfied almost surely. Now, what I cannot do, however, is stop this algorithm and say, oh, now pi dagger of lambda k, that's the Lagrangian maximizing policy, converges to pi star. Okay? So let me go again, right? So here I am introducing a stochastic version of the algorithm that I discussed in the previous section of the talk. I can prove the same algorithm now in probability, right? Because, well, the gradient update is stochastic. Not in probability, sorry, almost surely in probability. And I am now pointing the fact that I didn't point before, that this sequence of actions does solve the problem that I want to solve. I cannot, however, stop the algorithm and be done with it, which is what we typically do in learning, right? So we train, and after we train, we fix a policy. That doesn't work. But the sequence of policies does work, okay? Which brings us to what is the proposed solution, which is that in order to solve constraint reinforcement learning, instead of learning to solve the optimization problem, we can learn to maximize Lagrangians over a family, over a distribution of dual variables. Now that's what we call state-augmented constraint reinforcement learning, and let me tell you with this diagram why this is a good idea, or maybe explain it a little better. So this is the problem that we would like to solve, okay? So we would like to be able to, this is a description of the MDP. So here is the state, here is the action, this is the transition probability kernel, this is the state at time t+1. What we would like to do is to find this policy pi star, the one that solves this optimization problem. That I do not know how to do. I would like to say that nobody knows how to. That would be not entirely accurate, because I could solve this problem in occupancy measured space, for example. But you know, if you want to operate in policy space, we do not know how to solve this problem. The proposal here is the following. Instead of learning to solve this optimization problem, I will learn to maximize this Lagrange. Then, at execution time, I can augment the state with the Lagrange multiplier, and I can update the Lagrange multipliers myself, okay? Why do I need to do that? Well, because in order to implement these policies, I need to be implementing the dual gradient update. Thus, instead of having an MDP characterized by ST, the MDP is characterized by ST and lambda k, and the transition probability kernel, instead of being simply characterized by P, is characterized by P and this other P, which describes the evolution of the Lagrange multipliers. And in between, we have this policy, and you can see now that this is entirely workable. Why? Well, because now I can apply the theorem that I proved before, and since I am generating this sequence of policies, this diagram or the recursive application of this diagram will give you a solution of the constraint reinforcement learning. Now, of course, we still need to introduce a parameterization. That parameterization requires that we take expectation over some lambda distribution. This has the usual problems of off-policy reinforcement learning. There's a lot of practical challenges here that I am neglecting. But in any case, these challenges can be overcome, and you can end up with an artificial intelligence algorithm or a machine learning algorithm of this form. And really, the only thing that is worth remembering here is that instead of learning how to solve the optimization problem, we learn how to maximize Lagrangians, and we execute Lagrangian maximizing policies online. This works, by the way. This is just an illustration of that. It works in a very interesting way. So, which is through the use of policy switching. Okay, this would take me several minutes to explain. But if you have worked on wireless communications before, you know that optimal policies have this bang-bang behavior, right? So when I communicate, you need to shut up, vice versa. So what this state-augmented algorithm is helping you do is to switch policies at the right rate so that you actually end up satisfying your constraints. Okay. Let me, well, like if you guys were tired at minute 20, let us imagine at minute 40, right? But, just so you've been kind to me, let me give you another summary, okay? And in this summary, I'm going to also add the new fact. Let's go again through that summary, right? So the summary says that, yes, we should be formulating problems with constraints. Problems with constraints are not rocket science, right? Or actually, they're not Shakespeare. I mean, there's a lot of people that can do rocket science, only Shakespeare wrote Shakespeare. So I like to say that. So it's not a big deal to formulate a constraint learning problem. What is a big deal is realizing how useful these problems can be, how important they can be in terms of avoiding pitfalls of AI and in terms of solving or applying AI in physical systems. And it is also important to recognize that these optimization problems have significant challenges, or they pose significant challenges to the resolution, which come essentially from the fact that we're operating in optimization problems that are not convex. However, like for us, these optimization problems, they have either no duality gaps or small duality gaps. And if they have small duality gaps, we can operate in the dual domain and sort things out. Okay, so that's what I've been doing. And in order to sort things out, I first told you that, yes, indeed, the duality gap is either null or small. And second, that doesn't really mean that you can apply primal dual, as it is called, but you can modify primal dual so that things work out. Okay, and that's what I have done in the last 10 minutes, which is the introduction of this state-augmented algorithm in which I augment the Markov decision process state with dual variables, and I then proceed to update the dual variables myself. And this is very helpful because it allows me to change the problem of solving the optimization problem or solving the constraint learning problem into the solution of this unconstrained learning problem, which is the maximization of the Lagrange. And that can be applied and shown to solve the constraint learning problem that we wanted to solve in the first place. Now, the final technical part of the presentation that I want to cover is that I wanted to talk a little bit about the idea of resilience or resilient constraint learning, which is the name that we give to this algorithm or this equilibrium condition that sorts out the challenge of not knowing what the constraint level should be. Let me be more specific. Here is, again, our constraint reinforcement learning problem. I am trying to maximize this objective reward subject to these constraints rewards. And my requirement is that this has to be larger than C. But as any of you that has worked with constraint problems, you know that this is a little bit of a back and forth, right? I mean, I give you some C, maybe that C doesn't work, you change it a little bit, but that's a little antithetical to the idea of learning. I mean, the idea of learning is that you will learn the solution. So, typically the human is in charge of adapting this U. We would like the machine to adapt this U as well, okay? And that is what we are going to attempt to do. Now, in order to sort out what to do with U, let us remember the following thing, which is that if I increase U, meaning if the relaxation is larger, the objective loss will decrease because my constraints are less stringent. I'm giving you more power. I am reducing the required rate of your wireless communication customers. So that's a positive, that's a benefit, right? I mean, reducing the objective, that's good. Well, sorry about this. I mean, there's a typo here. This should be the other way around because I am maximizing, okay? So this should increase the objective. Now, the thing, however, is that, well, I mean, if you violate your constraints, you violate your constraints. I mean, that's a negative by definition, okay? So what to do? Well, the idea here is the following. I mean, let's introduce this equilibrium condition. H is some relaxation utility, and this is the start differential of your optimal objective with respect to the relaxation. And your equilibrium condition is to say that these two things should match. So what is the idea here? Well, I am showing you here three graphs. On the left, I have a problem that is easy. In the middle, I have a problem that is difficult. On the right, I have a problem that is infeasible. Now, and the utility here is just a U squared, so that gradient over there is just U. Okay, so what you can see here is this. I mean, this is the derivative of the objective with respect to the relaxation. So if the problem is easy, that relaxation moves a little bit. If the problem is of middle difficulty, the relaxation becomes larger. And if the problem is very difficult, the relaxation moves a lot. Okay? So this is a very sensible equilibrium condition. And of course, I hope that a lot of you are realizing that the reason why I am choosing this specific equilibrium condition is because that derivative is equivalent to the optimal Lagrange multiplier. And optimal Lagrange multipliers are measurements of how constraints are how difficult constraints are to solve. The algorithms that I have been describing, they will give you as a byproduct this optimal Lagrange multiplier. So, this is very consistent with the theory. And this is what we call the resilient equilibrium. This comes from the idea of resilience in ecology, which is, an ecosystem is resilient when it is able to adapt function. And this is what we are doing here. You tell me, these are my requirements. I tell you, I cannot satisfy these requirements. I'm going to do something else, which in a sense, is as little of a deviation as possible, or at least is something that an economist would claim is as little of a deviation as possible. An example of this is this idea of heterogeneous federated learning. So here you have, a bunch of different customers. They are collaborating to learn something. In principle, by the way, that's another interesting formulation of constraint learning. You could say, I am going to minimize the loss over all my customers. But if I give all of you a good policy, but my policy is terrible for me personally, that's little consolation to me, right? So we should not be doing company-centric AI, we should be doing customer-centric AI. And customer-centric AI is a constraint. It means I want this reward to be a small, I want this reward difference between me and the median or the average to be small. My explanation here was terrible, but here is the idea again. So, customer-centric AI means the following. So instead of minimizing the average reward, we minimize the average reward subject to the requirement that no customer is too far away from the average. Okay, so I am willing to suffer a little bit for the benefit of society, but not too much. Okay, good. Now, if you do that, you will end up observing lots of this nature in which clients, in which samples deviate more from the mean are relaxed more. Another interesting conclusions on another interesting behavior that you will observe is that the constraint violations of resilient solutions tend to cluster into a smaller region, as maybe you should have expected to happen. Okay, good. Now that brings me to the end of the talk. If you guys do not object, I would like to give you one final summary, and maybe I have earned the right to express a couple of opinions, okay? So this talk has been about the idea of learning under requirements, learning with constraints. You know, I don't know if you have ever seen this, but this is the diagram that you would see in a first course on systems engineering, okay? They will tell you, you specify requirements, you acquire data, you make a model, you choose your operational settings. What is great about AI, and this one's a personal opinion, you can go from data to operational settings without going through the model, okay? And I am a model kind of person, but I have to recognize that this is very valuable, okay? I like to think that I am expensive, right? So if I can be replaced by a machine, that's good for society, okay? However, there is something very important that is missing in this diagram. If you want to go from data to operational settings, which is requirements. I mean, we never talk about requirements in AI. So this personally, I find it unacceptable. Because I find it unacceptable, I have made it my mission to try and convince people to work on learning with requirements, and you can do that in both constraint supervised learning or reinforcement learning. Now, requirements, I believe, and I think I have some evidence to point out that they can be transformative in practice. For example, here we can improve the Pareto front of helpfulness and safety of a large language model. We can compose diffusion models better than other alternatives, deviating less from the pre-trained models. We can, I believe, most importantly, solve or utilize AI in physical systems such as wireless communications or power distribution networks. And finally, I like to say that we do it because it's useful, but also because it's fun. And requirements in AI, they do raise a number of interesting fundamental questions. And I've covered here the three that I have been able to find, but by no means I believe these are the only things that make this problem interesting. First is that even though these problems are non-convex, they have either null or small duality gaps. That is an interesting fundamental property that these problems have, an important structural property of these problems. Second, algorithms are not so straightforward as you would think they are. At the end of the day, you know, some version of dual gradient descent is what you should use. We can discuss in more detail why I say this, but I do think that there really is no other alternative here in terms of algorithms. But these algorithms have to be tweaked a little bit for them to work in practice, for example, through the use of state augmentation. And again, there's other ideas that you could implement here. And finally, something that I think is very promising is this idea of learning the constraints themselves. Because if I go back to this diagram, you know, what engineers do is not only that we specify requirements, we also kind of determine what requirements are feasible. That's the back and forth with our clients. So, you know, being able to automate the specification of constraints, I think is very important. Finally, I believe that I hope that the following three claims have been substantiated in this talk. Claim number one is that systems engineering and artificial intelligence are closer disciplines than is often recognized. And I think that this cuts it both ways. I mean, people in systems engineering do not recognize the value of AI for systems engineering and vice versa. And I think that we should use more AI in systems engineering and more systems engineering in AI. My second claim is that ignoring requirements is poor systems engineering, right? I mean, if you are a systems engineer, you ignore requirements, you will get summarily fined. And I think that because of this connection, which is, stronger than is often recognized, we can solve some limitations of AI if we incorporate requirements in AI. And finally, it's not just useful, but also fun. Okay, so these constraint problems and constraint reinforcement learning in particular, they are interesting mathematical objects. They are not convex, but they have a small duality gaps. And that, if you did not understand anything of my talk, I think is the most important message that I want you to understand. And now, yes, that is all. Thanks a lot for listening. And it's been a pleasure to be here.
If there's any questions, I'll please ask you to stand up and get there people come go through over the contract, please. Please go ahead. We are looking for the next talk. So I have a question regarding the first part of the talk where you connected constraint learning with alignment. So in wireless context, the constraints are usually very well defined. Even the power, how much we want to satisfy is very well given, and it has particular units which comes from the. It has visual need. But when it comes to alignment, usually the constraints are only in terms of reward value, and they are not very well defined. And even we are often confused what to put in the objective, what to put in the constraint. So and even the design of threshold is even very complicated. So how can, or is there any guidance regarding that from the analysis?
Yeah, so that's a very important question. So like in this particular problem here, right? I mean, there's something that I glanced over, which is okay. I mean, what is this CI? Because then I went on to talk about helpfulness and safety. And helpfulness and safety are, trained rewards, which are, who knows? So first off, I mean, let me give a critique, right? So that in principle is not my problem. I mean, people that are proposing these rewards, they should be proposing rewards with units, right? Because if I tell you the distance has to be less than 1 meter, 1 kilometer, so you would never say less than 1, but here we say less than 1, and we don't know what 1 is. But okay, that would be too easy of me to give you that answer. A more interesting answer is something like this. So for example, there are things here that you can translate into constraints that do not depend on that. For example, in safety, you typically have user preferences, okay, which tells you, answer 1 is better than answer 2. That is something that you can translate easily into a constraint because you would like the probability of answer 1 to be 1 minus epsilon and the probability of answer 2 to be 0. Okay, so there are situations in which you can get away without specifying this C. Something, like going back to this, and let me give you an example of that. Let's go back to this problem here, right? I mean, I could have formulated a problem of saying, oh, I want the KL divergence to be less than something. But what does it mean that the KL divergence is less than 0.01? I have no idea what that means because KL divergences are dimensionless. But I can formulate this problem, which I say, look, I don't know that, but I'm going to minimize the worst case. Right? So you could do something like this here. Okay, fine. These rewards, they can be of very different natures, but if they are of similar natures, I could try and minimize the worst possible case. Another example of this, I mean, there's some other rewards that have units. For example, the length of a response has a unit. There are also some other scores that do have units that could be. Thank you.
Related to what you have mentioned, that there will be an argument to solve the reverse problem, like this is really common that there is a constraint on the K divergence and maximum utility or rewards. But if we flip the problem and minimize scale with this constraint, is there anything to gain other than the using that we can specify CI? Is there anything additionally from
Okay, so let me see if I understand what you're saying. So this is the minimization of KL subject to reward constraints. So what is the other problem?
And then there is this standardized, unharmonized, situation that you
Yeah, if you formulate that problem, you should solve it using the same techniques that I described here, and that will work better than these other things that people do, right? Like, for example, as this Pareto optimality curve is shown, okay? The problem that you're specifying is actually literally the dual of this, the Lagrangian dual of this. So, the formulate, the solution of that problem will be similar to the solution of this problem. But yeah, to make a long story short, I mean, you can formulate that problem and you should solve it using some variation of dual gradient descent. Yeah, I have time. I mean, you guys are free to leave, everybody, any of you. I'm gonna keep talking with my friends. Yeah.
I had a question about the imposition.
Yes.
It looks it's something, it's a problem that might happen when you change this random multiplier and regular intervals, that you're kind of concentrating your failures in time.
Yes.
So you're meeting the constraint on average, but you have periods of time where you have like really high violations. So I was wondering if there's any solution to that. This is something.
Yeah. Yeah, that is a fantastic point. So here, I am pointing to this theorem here. So here we have P minus eta B squared over 2. Eta is the step size. If you is the step size in the dual domain. If you increase eta, sorry, if you increase eta, switching will become faster, and therefore you will suffer less from the problem at the cost of suboptimality. And that is a fundamental trade-off of all of these ergodic optimization problems. I mean, whenever you are solving something over time, there is a trade-off between making the switch fast enough and having enough optimality. And that trade-off is, as far as I know, unsolved.